What the heck is PivNert?
Okay, so I want to start talking about the ideal gas equation, which you guys know about Avogadro's law, Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, right?
Right.
Okay. So I'm going to duck back a little. I'm going to step back a little bit to kinetic molecular theory. Well, let's look at like a little container, a closed container that has some particles moving around in it, right? So they're all like going different directions. So what is something we know about these little particles traveling around? What are they doing to the wall of the container?
Putting pressure on it.
All right, so they're causing some kind of pressure on the wall of the container, right? It's probably some of you guys, maybe you remember this from earlier years, maybe not, but pressure is equal to force, the amount of force per area, okay? So the less area, the less volume, and the more force, the more pressure.
So wait, the less area and the more force?
Yeah, so if we squeeze the same amount at the same temperature into a tinier area, it's going to be a lot more pressure on that tiny area.
Okay,
right?
So then the bigger area and the less force equals the less pressure.
Yes. So the bigger area with the same temperature molecules, it's going to be a lot less pressure because there's a bigger space for them to travel in. Like if this was a closed container, this closed room, there's not too much pressure on the walls because it's a pretty big container. So if we're looking at collisions, as particles are moving around inside a little container, the faster those particles are moving, the higher the pressure it is. We know this from kinetic molecular theory.
So what happens if two little molecules hit each other?
They just bounce off each other. They're elastic collisions. They don't absorb any force. They don't stop because they hit each other or go faster or break. They just bounce off each other and keep going in the same direction, that in the opposite angle. They just bounce around. We assume. We can't actually see this, but we assume based on experiments that that's how it happens, right? So the faster the particles move, the higher the pressure because there are more collisions happening in that little container. Okay. Same is true if they're slower. There's less pressure because they're not hitting the wall as much. Right? Just some basic kinetic molecular theory. Remember these things, right? All right. So we know that temperature is equal to the average kinetic energy of a particle. So in other words, the temperature is the energy per particle. Okay. So we're looking at the higher temperature they are, the faster they're moving, the more energy they have, and so the more pressure they put on a container. So pressure is proportional, which we know this from all the laws that we've done. We know that pressure is proportional to temperature, okay, which means that I'm bad at remembering the names of them. It is. Nice job. Pressure is directly proportional to temperature, which we're looking at Gay-Lussac's law here. We know from Gay-Lussac's law that if pressure goes up, then temperature goes up, or if pressure goes down, temperature goes down, right? Right, good. I'm keeping you awake. This is good. I like this. Pressure is also directly proportional to the number of moles. So we don't have a law for that, but if I can draw a little picture. So there's a lot.
They look like little plus
stars.
signs.
Like little what?
Little plus signs.
So if these containers are all the same size, which one has the most pressure?
The first one.
The first one with the more moles, right? So
right.
Pressure increases if number of moles increases, and then increases from there. Okay. Pressure is inversely proportional to what? We've got a law.
Oh, Boyle's.
Yes, Boyle's law, which says pressure is inversely proportional to
Volume.
So pressure is also inversely proportional to volume.
Why is there one?
Because that's how you say inversely proportional.
Oh dear God.
All right, so I want to start. Let's see. I'm gonna have to piece in a lot of stuff here, but we're okay. So the ideal gas equation, the ideal gas law is what we're working on today, and it actually comes directly from the combined gas law. So interestingly, if you have the combined gas law memorized and you also memorize the constant from the ideal gas law, then you are set for gases forever. You remember those and you're good for ages. You know, you're all set.
What's the constant?
That's what we're gonna figure out right
Okay.
now. So if you know the combined gas law and the ideal gas law, you're set for life. We get the ideal gas law from the combined gas law because if we assume we have 1 mole of gas at STP, then we can actually plug in okay, so if we have 1 mole of gas at STP, what are my numbers here? What's standard temperature and pressure was?
273 Kelvin and 1 atmosphere.
Okay, so we can plug in T, right? So we can say 273 K.
Kelvin.
What do we have? We have 1 mole.
Yep.
Okay. You said pressure 1 atmosphere.
Mm-hmm.
Okay, that's pretty good. All right. And what is the volume of 1 mole of gas at STP? We did this in the last lab, and we'll do it in our butane lighter lab that we're going to do shortly. Very specific number. No, it's liters. Familiar yet? Okay. If I haven't said it before, I'll say it now. 1 mole of any gas at standard temperature and pressure has a volume of 22.4 liters. Okay. Again, 1 mole of any gas at STP has a volume of 22.4 liters. Always. That's why in the lab, in the molar volume of gas that we did, you did percent error on your volume of gas at STP and the actual accepted value.
0.082.
0.82? One more.
0.05.
1. Okay. Now, our number, this ends up being, this is our constant. Okay, we've just figured out what our constant is, but what are the units on this constant?
Divided by Kelvin and moles.
Yeah, so this is where it might get a little hairy. Our constant in the equation that we're going to use is atmosphere liters, Kelvin moles.
Is that Pivner?
Yes. Okay. So this is a little weird. R is a little weird. We took all the information we know about gases, about 1 mole of a gas at STP, which means it's at a standard temperature, a standard pressure. It has a specific volume and a specific number of moles, which is 1 mole. Okay. And so we get this crazy number that has 4 units attached to it. Okay, but if that constant goes into here, we'll find that as long as you don't forget where the units are supposed to be, they'll cancel out for exactly what you're trying to do. So
Well, R is actually this number right here. This is a famous number. Sometimes scientists give numbers letters, and they're famous numbers.
Okay, so whenever we see R, we're going to put 0.0821 if our pressure is in atmospheres.
Right. And so what you really need to do when you do problems of this variety is convert your pressure into
Atmospheres.
and your volume into liters, and your temperature into
Kelvin.
Kelvin. Always think Kelvin. Kelvin.
Always
Always.
Kelvin.
Always Kelvin.
okay, so let's do what we've done before with examples, and let's find what we know. We know pressure, right? Mm-hmm. We don't need to write pressure form. We know pressure, which is
2 a.m.
2 we know volume.
2 liters.
Good. What else we know? We know number of moles.
No.
No, that's what we're trying to find. So then we know R, right? What did you say it was?
0.821.
And what are the units on it again?
Okay, so it was pressure ATM times liters over Kelvins times
Kelvins.
Kelvin moles.
Okay.
I have a question.
Yes.
Is that always going to be 0.0821?
Alright, so this is what we know. What else do we know? T, temperature?
Is
What are you getting a calculator for?
because I need to put it in
Good
Kelvins.
point. Which it is
70,
273. 273 plus 30?
would be 303.
Okay. Let's color again. Alright, so let's plug the numbers in. So we got P times V.
So 2.
Now, this is where, like, if you haven't been doing it before, you watching, or you, if you haven't been doing it, you want to start writing units in. Okay? Because we've got these 4 units here, this crazy jumbled mess of units, and if you don't write units here, you'll I don't know what's happening. So we have 2 ATM times 2 liters, right?
Mm-hmm.
Equals number of moles.
Question
Mark.
times
R.
0.0821 ATM
What is it again? ATM
liters over Kelvin moles.
Times
303 Kelvin.
Alright, so I didn't exactly leave myself enough room, but we can rearrange this pretty easily, right? We're going to end up with 2 times 2 liters equals N, and we could take these 2 and divide them over here, right?
Yes.
So we end up with 0.0821 ATM liters per kmoles times we.
I have an answer for that problem.
So the question is, what is M?
4.
Or you can do 4 divided by 0.0821 divided by 303.
That's wrong. 4 divided by parentheses. No, this calculator. 821 times 0.1608.
Now, we're looking for number of moles, so the unit should be moles, right?
Yeah.
Let's prove it. Does it cancel?
ATM and ATM. Liters. Can you cancel the Kelvin and
Yep,
Kelvin?
sure can.
Okay. And then you're left with moles.
You're left with 1 over 1 over moles,
Well, that
which
looks
is
like
technically
just moles.
moles. So yes, moles. Yay!
Fun equation.
A very useful equation. So basically what we've done is from learning the previous equations and learning combined gas law and Pivnert, you can tackle any problem I give you if you know the last 2. Because combined gas law is good for if you have a change. Pivnert is good if you're trying to find one thing. If you're trying to find the volume of one thing. So when we just did molar volume of gas with combined gas law. We're going to do the next lab. We're going to do molar volume of butane with Pivnert.